what I also want to say about this, when we're playing with these derivatives, there's a few other things that end up manifesting, a few other physical observables. And I'm not going to derive these directly, but I'm just gonna briefly talk about them. So I'm gonna go. I had to give myself another page here. I ran out of room. Okay. So now we know that du equals pi t dv plus cv dt, and that was a result of partial of u with respect to v at constant t dv plus the partial of u with respect to t at constant v dt. Okay, and so we know when we did that, we got these two physical observables, constant volume heat capacity and internal pressure. So what about P? Okay, what about dP? So now I'm going to look at the total change in U with respect to P. So we're just going to apply the change in P to this whole expression. Oops, wait, hold on a second. What did I do? How does internal energy vary with temperature at constant pressure? Yes, so apologies. That's what we want to do. What about dP? So excuse me. So for now, I apologize. Let's think about how we have to. So we've held volume constant, we've held temperature constant. So now we're going to hold pressure constant. So I'm going to look at it in this way, okay? And you'll see why momentarily. Because what it does, I'm going to keep this pi t. So now this is going to give me partial of v with respect to t at constant p. So that's why we're going to do dt at constant p. Because this is the last, if you think about that reciprocal identity that I talked about in lecture 11a, this is the last variance that we have to do. Okay, and then now dt over dt cancels, so that ends up just being plus cv. Okay, and so now we're going to play with this relationship, partial of v with respect to t at constant p, and as it turns out, that's the slope of Charles' law. Okay, and so there's some other physical observables that manifest from this partial of v with respect to t at constant p. So just like we got out the constant volume heat capacity and the internal pressure, there are two more physical observables. I'm not going to derive them directly. I'm just going to kind of show you the result. But they are a manifestation of thinking about how the volume changes with respect to temperature at constant pressure, or, right, even as we know, how does volume change? So let's chalk that up. So we can say this, or how does the volume change with respect to pressure at constant temperature, right? If I switch the order of those two parameters. And so the result of that is two of these coefficients, one known as the expansion coefficient, one known as the isothermal compressibility. Okay? And so again, I'm not deriving where these come from, but you will notice they contain that relationship. So the expansion coefficient is a result in the change in volume with respect to temperature at constant pressure. So in other words, the expansion coefficient gives us how the volume of a sample changes with changes in T, right? So as we heat up a material, we generally think of it as expanding, right? As we cool the material down, we think of it as compressing, okay? Similarly, we have this thing called the isothermal compressibility. And you notice now, this is looking at how the volume of the sample changes with respect to changes in pressure. So volume of sample changes with changes in P, okay? And so I've got some representative materials here. Benzene, diamond, lead, and water. And let's think about what these things mean. So if I compare the value of benzene to the value of diamond, and this is the alpha coefficient, what does a big alpha mean? What does a little alpha mean? Well, for benzene, a big alpha means that benzene is going to be sensitive to changes in volume with respect to temperature. So if I take a sample of liquid benzene and heat it up, we're going to see changes in volume to the benzene much more than we're going to see the changes in volume of the diamond. And that makes sense, right? Benzene is a liquid at room temperature and pressure, right? So these are the values at 298 K. So it'll be much easier to expand a sample of benzene than it will be to expand a sample of diamond. And we're not talking about a whole lot of expansion. Look, this value is 10 to the negative fourth per Kelvin, okay? So these are small values, right? So that alpha, is 12.4 times 10 to the minus 4, okay? So now what about isothermal compressibility? So again, compare benzene and compare diamond. It's really the same thing. It's saying that at constant temperature, I can squeeze the hell out of a sample of benzene and get a much more noticeable volume change than I can for a diamond. And that makes good sense, right? That makes really good sense, okay? So let's see. So I'm just going to very quickly show you how we can use this in calculations. So and I'll just do that for the isothermal compressibility, okay? So I'm going to rewrite this here, and I'll show you how we can take advantage of the fact that this is a partial and what we can do with it. And so this is what I call divide and conquer. So let's get the like terms with like terms, okay? And so I'm going to put over on this side negative kappa T dP equals dV over V. Okay, so I just separated those out. And then now what I can do, I'm going to do my work over here. I can integrate from initial to final of negative kappa T dP. And I can also integrate from initial to final of dV over V. Okay? And so what do I get? Well, over here, on this side, I'm going to get a kappa T times delta P. Right? Pretty straightforward. And so what am I going to get over here? And so, sorry, there's a negative sign. Well, here I'm going to get natural log of VF over VI. So how can I make that useful? Well, take E of both sides. Okay, and so when I take E of both sides, I'm going to write this way down here. I got E to the negative kappa T times delta P. All right, so I'm going to keep that there. And when I took the E of this side, it's VF over VI. And I'm going to do a couple algebraic steps, so make sure you're okay with this. So then I'm going to move VI over to this side. So that's going to go in front of the exponential. And then finally, that's VF. All right, cool. So now what this formula gives me is a way of calculating what would the final volume be, given that I know the initial volume and the change of pressure, right? And I can do the same thing for the expansion coefficient. And what you would find for these things like benzene, I mean, we talk about these like liquids and solids being the, incompressible fluids, right? Well, I mean, if you isothermally compress a sample of benzene with 1,000 atmospheres. So if I make delta P 1,000 atmospheres, you can noticeably compress that liquid. You can shave like 10 milliliters off of a liter volume of benzene with 1,000 ATM. That's kind of impressive when you think about it. We normally define these liquids as incompressible fluids, but given enough pressure, we can squeeze the hell out of these things, okay? And obviously, you can tell that benzene, it's like a factor of 100 greater compression than diamond. And, right, similarly, it's a factor of nearly 1,000, 1, 2, 3. Yeah, it's nearly 1,000-fold in the expansion, all right? And so there's some nice intermolecular forces that we could talk about going on here. You also notice that water is not nearly as compressible or expandable as benzene, and that's due to the hydrogen bonding network, right? Benzene is like, flat, right? Like we can stack it up, okay? So benzene is fairly compressible as a liquid. Okay, I'm gonna move on.